You've seen lasers everywhere, right? They're in the barcode scanners at the supermarket, those little pointers we use in meetings. They're even used in super precise surgeries. But have you ever really stopped and wondered what makes that tiny, super intense dot of light so different from, say, the light from a plain old light bulb? Well, let's get into it. So this is the big question. A light bulb just throws light all over the place, right? It lights up a whole room. A laser, though, creates this tight, focused beam that seems to go on forever without really spreading out at all. So what is the secret here? It all comes down to three very special properties that make laser light unlike anything else. So what is it? What's the secret sauce that makes laser light so unique? Let's break down its three key properties. Okay, first up, laser light is monochromatic. Now, mono means one and chroma means color. So what this means is that all the light in a laser beam has the exact same wavelength. It is one pure specific color. Unlike the white light from a bulb, which is really just a big jumble of all the colors of the rainbow, a red laser is just that one perfect singular shade of red. Second, and this is a big one, it's coherent. This one's a little bit more abstract, but honestly, it's the real game changer. Think of light waves like soldiers marching. In normal light, like from a bulb or the sun, the soldiers are just a chaotic mob, right? They're all shuffling around, completely out of step. But in laser light, they are a perfectly disciplined army. Every single wave is marching in perfect lockstep. All the peaks and all the valleys are perfectly aligned. And this is what gives it such an organized, concentrated power. And third, because all those waves are the same color and they're moving in perfect formation, laser light is highly directional. It travels in an incredibly straight, narrow beam with almost no spreading out at all. This is exactly why your laser pointer can make a tiny little dot on a wall way across the room, while even a powerful flashlight beam just becomes this big, wide, fuzzy cone of light after just a few feet. And hey, for any of you students watching, here's a little pro tip for you. These three properties, monochromatic, coherent, and directional, this is a classic exam question. So really lock these three terms in. You'll be glad you did. Now, here's what's really interesting. The word laser isn't just some random name somebody came up with. It's actually an acronym, and it describes the entire process used to create this special kind of light. It's like the blueprint is hidden right there in plain sight. So come on, let's decode it, letter by letter. L is for light, of course. That's what we're making. Simple enough. A is for amplification. Okay, now we're getting somewhere. We're not just making light, we're making it way, way stronger. S is for stimulated. Now this is the absolute heart of the whole thing. It tells us this is not a natural process. It has to be kicked off or stimulated into happening. E is for emission. An atom is giving off or emitting that light. And R is for radiation. Now, don't let that word scare you. In physics, radiation is just the term for energy that travels in waves or particles, and light is a perfect example of that. So, there you have it. Laser stands for light amplification by stimulated emission of radiation. It's all right there in the name. We are amplifying light using a very specific process called stimulated emission. And you know what? Understanding that process, that's the key to everything. So to really get to the heart of what stimulated emission is, we need to take a quick look at the three ways light and atoms can interact with each other. It all comes down to what the little electrons are doing inside an atom when they get hit with some energy. First, there's absorption. Pretty simple. An electron in an atom gets hit by a photon of light, it absorbs its energy, and it gets kicked up to a higher, more excited energy level. Then you have spontaneous emission. Now, that excited electron, it can't stay up there forever. So whenever it feels like it randomly falls back down and it spits out a photon in any old random direction. This is basically what's happening inside a light bulb, just billions of atoms creating total chaos of random light. But then there's the third process, the one that changes absolutely everything, stimulated emission. And this is where the magic happens. In stimulated emission, you have a photon that flies by an electron that's already in that excited state. The photon's presence kind of nudges or stimulates the electron to fall back down and release a second photon. Now get this, here's the kicker, the absolute miracle of this whole process. That new photon is a perfect clone of the first one, a twin. It has the exact same energy, the exact same phase, and it's traveling in the exact same direction. One photon becomes two identical photons. And that is how you get coherence and amplification. That's the beginning of the chain reaction.
Okay, so if stimulated emission is so incredibly powerful, how do we make it the main event? I mean, in nature, that random spontaneous emission and absorption are happening all the time. To make stimulated emission the star of the show, we have to force the atoms into a very specific and very unnatural state.
Under normal conditions, in any group of atoms, most of the electrons are just lazy. They're chilling in their lowest energy state where it's stable. To get a laser to work, we have to completely flip that on its head. We need to create a situation where there are more electrons in that high-energy excited state than there are in the lower one. This bizarre, totally upside-down condition is called a population inversion.
And this is maybe the most important takeaway of all. Creating a population inversion is non-negotiable. Without it, any photon flying by is more likely to just get absorbed than it is to cause stimulated emission, and the whole process just dies out. You absolutely positively must have a majority of electrons ready and waiting in that excited state.
All right, we've got all the ingredients. We know we need that special process, stimulated emission, and we know that requires this weird, unnatural state called population inversion. So now let's see how they all come together inside an actual working laser. So basically, every laser, no matter how big or small, has three basic parts. First, you've got the active medium. This is just the bunch of atoms we're going to excite, maybe a gas or a special kind of crystal. Then you need an energy source to pump that medium full of energy and create our population inversion. And finally, you have an optical resonator, which is really just two mirrors facing each other, designed to trap light and bounce it back and forth. And here's how it all plays out. Step 1, the energy source pumps the active medium, forcing it into that population inversion. Step 2, a single photon, maybe from a random spontaneous emission, zips past an excited electron, and bam! It triggers stimulated emission. Now you've got two identical photons. Step 3, these two photons hit two more excited electrons, now you've got 4. Those 4 create 8, then 16, 32. It's an avalanche of perfectly cloned photons. And those two mirrors trap this growing light, bouncing it back and forth through the medium over and over and over, amplifying it like crazy with every single pass. And finally, step 4, one of those mirrors isn't a perfect mirror. It's partially reflective. So it lets a tiny fraction of this incredibly intense, perfectly organized, coherent light escape as the laser beam we see. And that is really it. You go from 3 simple properties to an atomic chain reaction trapped between 2 mirrors. As our source material so nicely puts it, if you followed along and you understood these core ideas, then the topic of lasers really shouldn't be intimidating at all. I mean, it's just an amazing piece of technology, isn't it? It's all built on forcing atoms into a totally unnatural state just to create this perfectly ordered form of light. It really makes you wonder, now that we have this incredible level of control over one of the most fundamental things in the entire universe, what does that make possible? Now that you get how to perfectly control light, what new possibilities can you imagine?